riddle to start things off. What never gets tired no matter how long it runs? Water, H2O, one of the great riddles in chemistry and the natural world. It's the only natural substance on Earth found in all three common states of matter: liquid, gas or vapor, and solid, ice. Which is another riddle. Unlike ice, almost all other substances behave like steel. When in liquid form, like molten steel, they're less dense than when in solid form. As steel changes from liquid, cooling into a solid, say a steel beam, it condenses, concentrates, gets more compact.
The atoms come in closer to each other, and overall the material becomes more dense, becomes more heavy for a given volume.
Drop the steel beam into the molten steel and it will sink. But drop a piece of solid water, ice, into liquid water, and whether it's ice cubes in your water glass or icebergs in the Arctic, it floats. In solid form, H2O is less dense, lighter than the same amount of H2O in liquid form. Because as you're about to see, when water freezes, it doesn't contract, it expands. Now, to puzzle out the riddle of ice, look at the H2O molecule itself. Two smaller atoms of hydrogen bonded to one larger atom of oxygen. H2O is a polar molecule. The same way our planet has two opposite poles, the H2O molecule has two polar opposite sides. One side has a slight positive charge, the other a slight negative charge. You've probably heard that opposites attract, so the slightly positive hydrogen side of every H2O molecule is going to attract and be attracted to all the slightly negative oxygen sides of other H2O molecules in all directions. These bonds, called hydrogen bonds, are what hold water together. And as you know, water flows easily. In liquid state, the H2O molecules are making and breaking those bonds constantly. Imagine massive numbers of H2O molecules in a hot dance club, dancing so closely and wildly that they're constantly making and breaking contact with each other.
There's a lot of motion, there's a lot of energy, and they're not able to lock onto each other very well.
But watch what happens if the temperature drops. The energy level does too. The H2O molecules move more slowly, spaced further apart as if at arm's length. This is the water expanding as it freezes, which is at 0 degrees Celsius or 32 degrees Fahrenheit. That's water's freezing point, the temperature at which liquid water becomes solid water, ice. As the mass of H2O stops slam dancing and starts doing more of a molecular minuet, the water molecules are able to make longer-lasting connections, hydrogen bonds, with each other. The molecules freeze in place, arms locked, in six-sided or hexagonal groups that connect to form a 3D network called a crystal lattice.
Chemists will sometimes work weeks and months and years to get a single crystal of their compound or maybe a protein, and then you go by a frozen puddle and you can see one crystal of ice that might be 2 feet long. And it's just amazing.
This crystal lattice structure explains why H2O is less dense in solid than in liquid form, which is called water's density anomaly, by the way.
As you lock one water molecule to the next and the next and the next, you build up this network that actually has a lot of empty space.
All that empty space means there are far fewer H2O molecules in, say, a cup of ice than in a cup of water. Fewer molecules means it's less dense, which is why ice floats. But ice is no lightweight when it comes to strength. The Titanic only brushed past an iceberg on its fateful voyage in 1912, but that was enough to open fatal slits in the ship's steel hull. Water, as it freezes, expands with enough force to crack rock, burst pipes. Cutting through layers of ice can require axes, chainsaws, 3,000-ton icebreakers. As much as researchers know about ice, there are still unsolved riddles about what really happens on the surface of water and ice, about ice on other planets, moons, and asteroids. Think of this story as just the tip of the floating mass of H2O in solid form.